In this short video, you will learn how to switch from deterministic to probabilistic finite element analysis in ZSoil+R powered by UQ Lab, where you will see how to perform sensitivity and reliability analyses. Consider the following simple example of a 4-meter-high vertical cut. The unit weight of the soil is equal to 16 kilonewton per cubic meter. The cohesion is equal to 16 kilopascals, and the friction angle equal to 30 degrees. There exists an analytical solution for the corresponding safety factor derived by Terzaghi, which results in 1.66. If you perform a deterministic analysis with ZSoil, you get a safety factor of 1.55, together with the corresponding mechanism of failure. Now we switch to ZSoil+R, where we define our input variables as probabilistic. These are the friction angle and the cohesion. We assume a Gaussian distribution for the friction angle with a coefficient of variation of 10%, and also a Gaussian distribution for the cohesion with a coefficient of variation of 20%, which gives a standard deviation of 3.2 kilonewton per square meter. We will also define a correlation between the two input variables of -70%. So this is a negative correlation. In a next step, we generate samples. For this problem, let's generate 50 samples. For each sample, a pair of cohesion and friction angle is drawn from within the pool, defined by their probability density functions. The 50 resulting pairs of cohesion and friction angle will be the input parameters for one finite element calculation each. Once all of the 50 samples are defined, we can compute them. First, it creates the 50 input files for ZSoil, and then they are computed. The computation time depends on the performance of the machine you are running the samples on and the size of the FE model. The progress is indicated here. In our case, the samples will be calculated in less than 2 minutes. Let me fast forward to the end of calculation. Now that all the samples have been computed, we can define a quantity of interest, which in our case is the safety factor. Then we can review the sample results and see each input pair of friction angle and cohesion and their corresponding factor of safety. This set of results from all the computed samples now allows for the creation of a so-called meta-model. Such a meta-model is a continuous approximation of the response of the finite element computations, which are discrete. Using the computationally much cheaper meta-model enables us to perform a Monte Carlo simulation and run hundreds of thousands of computations in order to find, for example, the probability of failure of our vertical cut. The quality of the obtained meta-model is indicated here by this value, called the leave one out error. In our case, it is less than 1%, which means that we are dealing with a good meta-model. Now that we have the meta-model at our hands, we can, for example, conduct a sensitivity analysis with Sobol indices. Such a sensitivity analysis will tell us which is the most influential input parameter on our quantity of interest, the safety factor. We find that the cohesion is more influential on the safety factor than the friction angle. The reason for this may be because the cohesion has a greater coefficient of variation than the friction angle. Finally, we can perform a reliability analysis, again using the meta-model. For that, we have to define a criterion on our quantity of interest. We would like to know the probability that the safety factor is smaller than 1. The results are displayed as a histogram of computed safety factors. The mean lies at approximately 1.5, and the probability that the safety factor is less than 1 results in about 0.3%.